Welcome to a mathematical wonderland. We're going to talk about induction, and I'm going to try to do my best to not have this incredibly mathematical and only a little bit mathematical, but this is a big thing in math, especially in like number theory and stuff. And it's a powerful way of proving things. But don't worry, we're going to prove more than just some math stuff. So something that I had actually never heard of before, but the textbook author calls out, is he actually calls this, maybe a little jokingly, maybe a little truthfully, proof by recursion. Because that's really what induction's all about. Is we're talking about something for like a bunch of natural numbers, like 1, 2, 3, 4, 5, right? If we're trying to prove something for a bunch of numbers, that's really what we're doing here. Basically, we're just saying, all right, let's prove it for a subcase, and then let's prove it for a subcase of that, and then prove it like, essentially we're just breaking it down into smaller and smaller proofs. He says we're constantly passing on the responsibility to someone else. We'll show in the next video how it's kind of like a series of dominoes, but basically it's like a recursive proof in a way, which is pretty cool. Okay, so we'll talk about we'll start this video by kind of introducing what kind of problems can we use this method on. The next video is when we really introduce the method more formally. But yeah, again, the overview of what we're doing is essentially we're going to prove this for one number. And then if it's true for one number, is it true for the next? And now you can see, right? You can see that if we have these two things, then we can say some really powerful things, right? If it's true for one number, and if we know it's always true for the next number, well then, okay, well it's true for the next number, and then 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 the next number. And again, this one doesn't necessarily have to, oh my gosh, my cat is jumping off my desk with a lot of force and again, this doesn't have to be the same number. We'll get into it more later, but this is kind of the outline. But we're going to start by just practicing, how do we put things in the right form? All right, what kind of problem can we use mathematical induction on? And here's what we have to do. It must be a predicate. So remember, predicates are just propositions, but they're kind of like functions. A predicate is a proposition about anything inside of it, right? So it must be a predicate about natural numbers. All right, we're not going to deal with fractions here or negative numbers. All right, so let's look at what I mean. Let's do some examples. So we have three things that we might want to prove. The textbook uses the first example, but that's not actually true, so we can't prove it. But if we did want to try to prove it and say that in Washington State, all legal drinkers can vote, how might we use induction? Well, we have to put it in the right form. And again, I haven't mentioned what induction is. We're just getting practice putting it in the right form. We need a predicate, and we need this to be about natural numbers. So if we're thinking of voting age and drinking age, right, we can think about age in years. So we could have a predicate be like vote of n, and we're trying to prove this is true. And let's say this is the predicate that people of age n can vote. So if this were true, and again, this is not actually true, we could say that, yeah, people of age 21 can vote. And then if you're at some voting age, then next year you can still vote because you'll still be at that voting age. We're not aging backwards. No Benjamin Button situations over here, is how we would approach it. Over here, how can we phrase this as a predicate about natural numbers? Remember, if you are not familiar with this, this is summation notation. This says we're adding up a whole bunch of i's. We're adding up a whole bunch of i's, starting with I equals 1 and going all the way until I equals some number x. So So really, this is a shortcut for adding up 1 plus 2 plus 3 plus 4 plus 5 plus 6. And it's just whatever that last number is times the last number plus 1. So if you wanted to add up all the numbers between 1 and 100, for example, that would be x is 100. It would just be 100 times 101 divided by 2. So how would we do this? Well, we could let P of n be the proposition that this is true for x equals that n. All right, and then we could show that it's true when n is 1. That would be very easy. And then if it's true for any n, would it also be true for the next one? And again, we'll get into more examples, but we're just practicing how can we frame questions to use induction on. All right, and the last part is, again, and how we're doing that, is we're just getting practice putting statements into predicates about natural numbers. All right, the last one, number of leaves in a perfect binary tree is one more than the number of internal nodes in that tree. Is that true? Wait, what is a perfect binary tree again? Remember we had different levels of like thickness of trees, and the thickest was a perfect binary tree. Binary tree meaning, you know, you have left nodes and right nodes. Everything is, you only have 0 through 2 nodes, and it's always very clearly defined as a left or a right node. A perfect binary tree was one that every node had 2 children, and the bottom layer, the bottom depth, really was full. Okay? So they were things that looked... This is an example of a perfect binary tree. If we added another layer, another depth, we would have to add 8, because that would have to be full, essentially. Okay? So this is saying that the number of leaves is one more than the number of internal nodes. And yeah, you can see in this case, it's true. We could prove that for any binary tree, any perfect binary tree, and we will. Okay, how would we do that? Well, it's going to be the same ideas. But here it's a little tricky. What is our n? You don't really want n to be the number of leaves or the number of internal nodes. That's going to be a little weird. Although you could probably do that. But an easier way would be to let n be the height of the tree. So let P of n be the proposition that this is true for a perfect binary tree. Well, actually, we don't need to say that. It's redundant, but that's fine. A perfect binary tree of height n. All right. And I said natural numbers. That's not quite true. It's non-negative integers. So natural numbers, 0 is okay too. Technically, the natural numbers don't include 0, but 0 is okay. We can have a tree of height 0, and that is what indeed what we'll start with when we do this. So I don't really like how he structured this, because we haven't really talked too much about what proof by induction is. This is kind of the idea. If we ever want to prove something that's true for a bunch of natural numbers, we'll just prove it for one and then say, well, can we show that if it's true for any number, is it always true for the next? And then the idea is we have to be able to frame the question as a predicate about natural numbers or 0. And we'll see in the next one what we can do with it. Spoiler alert, we can do stuff like this to prove this. All right? So take it easy. Let me know if you have questions. Have a good one.